So, hello everybody and welcome to my talk. Today we are going to discuss about the process of bytecode interpretation and the process of execution and compilation of the bytecode. Hands up if you are familiar with the topic first. Good, good. We have an interesting audience. And hands up if you are a performance engineer. Absolutely nobody. Okay, after this topic, you will get a bit familiar with some tips and tricks, what happens during the runtime in the HotSpot JVM. So maybe it might open some doors. You may be patient after this topic to search more and to read more on the topic. My name is Balos. I'm software architect for Luxsoft. I'm technical trainer for the training department in Luxsoft, and I teach Java performance and tuning and software architecture methodology course. What we have in the agenda for today, we'll understand the bytecode, what is the bytecode, we'll understand how to disassemble the bytecode, we'll see and we'll understand the bytecode execution workflow during the runtime. We'll discuss about the just-in-time compiler. We'll check the native code out of the bytecode. We'll have a demo, some Java samples to test and to prove what we are going to discuss on the theory perspective, and we'll close with some micro-benchmarking suggestions. Okay, before to start, let's quickly sum up what's the JVM. What is the Java Virtual Machine? Java Virtual Machine, it's mainly a process for our application code. It's a container that has a built-in memory management system. For example, the garbage collector, it's a built-in memory management system. It provides robust and secure execution. It provides robust and secure execution, for example, because the class loader verifies all the bytecode before it is effectually run. More than that, we don't have any memory address during the runtime. Everything is resolved through symbolic references. The last one says it's base stack implementation. What's the base stack implementation? Base stack refers, in fact, to the fact that HotSpot pushes and pops the operand on the stack. In order to achieve arithmetical and logical operations, there are a lot of pushes and pops on the stack. Now let's focus a bit on the Java-C. Java-C, I would say it's half of the compiler. It's not quite a compiler. Why is not quite a compiler? Because Java-C gets the source code, the Java source code we have here, and transforms it into the bytecode. And the bytecode is just an intermediate representation. It's not the final shape of the code that we benefit of. At the bytecode level, there are a lot of opcodes. And each opcode is stored by a byte. That's why it is called bytecode, because the opcodes are stored, are handled by a single byte. And these opcodes are organized in families. We'll have a bit of detail later on about the opcode families. An interesting thing is that at the bytecode level, we don't have any memory access. We don't have any registry access. And at the bytecode level, we don't see any high-level features that we have at the Java level. For example, all the commands are erased. All the for and while loops are desugared into jump executions, into dispatch executions. Java P, sorry for this. Okay, Java P, it's the reversed way. What it means, I have the bytecode initially, and through Java P, I can disassemble my bytecode into a human representation way to check what are the opcodes, how it looks like. I can analyze the bytecode, and so forth. JDK provides by default the Java P tool, which is quite an interesting one. By default, it shows only public and default methods without private. If you are interested in disassembling all the private methods, you have to use -p. If you are not a fan of command line tools, I would suggest to use for Eclipse, there is a bytecode visualizer plugin, and for IntelliJ IDEA, there is ASM bytecode outline. But let's take a look what we have discussed until now. We have initially the source code, and for the source code, we have this trivial method that receives two parameters, does the sum, prints the sum, and returns the sum. We compile this code by using javac, and we end up with this .class file. If we open the .class file, and if we translate the content into hexa, the .class file has a specific format. The .class file, it's not something really random. And I'll start to briefly describe, for example, the beginning of the class file. It starts with magic. Magic is the hard-coded value that spreads across the first 4 bytes, and it is hard-coded to Coffee Babe. It's the same for all .class files. Now, what's next? We have the minor version, and we have the major version. The minor and the major version are in charge with checking the compatibilities between the JDK versions. For example, in my case, I have the major version as being 34, which means my .class was compiled against 1.8. If I'm going to run the same .class file against 1.9, it won't work, because the check is mainly done based on this major and minor version. What we have next, we have the runtime constant pool. We'll discuss about it. We have information about fields, about methods. We have information about implemented interfaces. We have information about the superclass. And if we decompile this by the Java P disassembler, we'll get the bytecode. So mainly, this is how the bytecode looks. And this load, add, store, these are the opcodes I was referring to in the previous slide. Now, let's see how the opcodes are organized in families. There is an invocation opcode family. It's in charge with all invoke methods. We have here invoke virtual. Invoke virtual is for invoking a virtual method. A virtual method is mainly a method that could be overridden. We have as well invoke interface. Invoke interface is when I'm invoking a method that belongs to an interface. We have invoke special. Invoke special, it's mainly for private methods or constructors. We have invoke static for invoking static methods, and we have invoke dynamic. This invoke dynamic will have a funny example with it. It's mainly for lambda invocations. We have another opcode family for arithmetic. In regards with this, there is add, subtractions, divisions, multiplications. We have as well the family for load and store. Load, it's mainly getting a value from a local variable array, getting a value mainly from somewhere, and adds that value on top of the stack. Loads, LDC stands for load a constant out of the constant pool and push that constant on top of the stack. Store is the reverse of load. Store means get the top of the stack and moves it back to the local variable array. And dup, we need dup, which is duplicate, because in few cases of invoke methods, the top of the stack it's destroyed, and we lose the reference. For example, when we create a new interface, by calling invoke special, for example, once the instance is created, the stack it's discarded, and we lose the reference to that object. And that's why we need this dup before calling the invoke special. Okay, let's see how it looks like. So initially we had this method, add method. We compiled the method and we disassembled the method. And this is the bytecode. Now, if we take a closer look over the bytecode, we see some kind of indexes. This index, for example, the 3 index, it's an index into the local variable array. Now, a bit of context before explaining this, how it works. Every time a new method is invoked, a stack frame is pushed to the current thread stack. So every time we call a new method, a new stack frame, it's pushed. It's added into the current running thread stack. What is the local variable array? Local variable array contains all the fields locally declared. It starts with a reference to the current instance. If it is static context, there is no this anymore. It continues with 198. These are mainly the arguments received by the method. So it starts with the arguments, and after the arguments are all the fields locally declared into that method. What is the operand stack? The operand stack acts like a workspace. It mainly does a lot of pushing and popping of operands on the stack. To be more specific, let's start by describing how it looks like. For example, I have here A and B, and I'm doing the sum of them. The bytecode is like this one. A stands for integer. So what does iload_1? Iload_1 adds the integer out of the first index of local variable array and pushes it on top of the stack. The iload_2, it's exactly the same. This time the number is retrieved, it's grabbed from the second index of my local variable array. add replaces the top of the stack by the sum of those two elements. So now I have in the top of the stack the sum of the elements, and the last opcode is I store 3, which means push back the number, the sum of those two numbers, push it back into the local variable array into the third entry. This is how it works during the interpretation phase in regards with the bytecode. Some simple scenario, but I think it's really relevant. Now, we discussed about how it works in regards to the local variable array, but let's focus on another kind of instructions, the invoke families. For example, we have here invoke virtual under 73. That 73, it's a reference inside the runtime constant pool. What is the runtime constant pool? The runtime constant pool acts like a symbol table. It's a symbol table that contains, for example, string literals, integer literals, floating points, references to other fields, methods, and so forth. It is mainly an ordered set of constants used by type, and each entry it's stored by using 2 bytes, and a reference, an entry inside the runtime constant pool, it's done through the index. It's like an array. We can get elements out of it based on the index. And the fundamental purpose of the runtime constant pool is that it plays a fundamental role during the runtime in the process of resolution, of dynamic linkage for the symbolic references. Let's have a bit of practice to understand it better. For example, we have this invoke virtual 73, which is mainly for printing my sum. I'm calling a virtual method that prints my sum. 73 corresponds to this entry inside the runtime constant pool. So here what we have a reference to a method which is resolved by this class index, which redirects here, and further I have to check out to spot the name of the class, which is this Java P sample based on the second entry in the runtime constant pool. What I know up to this time is that I'm calling a virtual method that belongs to that class. But what's the method name and its signature? For that, I have to continue my resolution process by getting the name and the type. And for the name and the type, I'm redirecting. I'm checking the 74th entry, which is resolved by 29, the name of the method, which is here. So it's print and the type of it. So it prints, it returns void, and it receives an integer. Getting back to our initial invoke virtual 73, after all this lookup process at the runtime, we know that we are going to call a print method that returns void, receives an integer, and that method is defined into the Java P sample class. Now it's a bit of fun. We'll see basically what exceptions are handled at bytecode level. At the bytecode level, there is a lot of information. For example, this exception table, it's part of that. The exception table, it's searched through every time a new exception is thrown at the code level. And let's see how it works. We have this reminder method that receives 2 arguments and does the reminder. Any exception encountered by this, and if any exception of this arithmetic exception type is encountered, it is caught, and basically a new type of exception is created and is thrown away. If we focus on the exception table, what we have here, the exception table says mainly any exception that occurs between 0 and 2, because 3 is exclusive. Any exception that happens between 0 and 2, and if that type of exception is arithmetic exception, I have this handler for managing, for treating the exception. If we take a look over the bytecode, these PCs are in fact some indexes into the code array. What it says, any exception occurring between 0 and 2, I have to check that exception, and if the exception is of type arithmetic exception, I have to continue with the fourth, because here is my handler defined. What happens if inside the exception table I don't have any finding? There is no exception defined. What do you think? Sorry? Yeah, the exception is thrown back to the caller, the stack frame is discarded, and inside the caller there is no exception handler into the caller. It is propagated back and back and back until we have an exception handler for it. Good. Now let's have it a bit more interactive. Let's have a bit of fun today. We had initially this MyDouble class. MyDouble class implements an interface. I compiled this class, MyDouble, and I disassembled the code using Java P. And once I have this disassembled code, I ended up with this representation of my class. So basically, it's the constructor and 2 methods. Can you please spot out few, let's say, ambiguities in the code's ambiguities? What's wrong with this? Because if we are going to compile it back, it doesn't work, for sure. And how's that possible? What are the first spots you can? Yes. So we have the same method declared twice. This is one, very good. The other? Volatile, very good. Yes, I'll explain you why we have volatile. First, we have 2 methods having the same signature. By signature, I mean the name and the parameters, because we are using the generics. And the JavaC compiler automatically adds the default method bound to object because of the compatibility against the row types. Now, what's the explanation for volatile? Here, volatile, it's a bit tricky for the programmers. It doesn't have any sense. It doesn't puzzle the Java virtual machine. Volatile here, it's for the bridge methods. Bridge methods and volatile identifier are the same. They have the same identifier in modifier.java. That's why here it should have been written bridge, not volatile. But because the volatile and the bridge have the same identifier into modifier.java class, that's why. It's just a confusion for us, but the JVM can handle it. For the JVM, there is no difference. OK, very good. Here is my initial public class that was compiled and disassembled. The second quiz for you. I had initially this Java p-outer class, which contains a private void foo method and an inner class that refers to this private method foo. I compiled the Java p-outer class, and I have disassembled the same process as previous. And if I look in the disassemble code, I figure out this access $0 method, which is not my method. It's not the method I have defined initially. How is that possible? This is the question.
So it's a synthetic method that gives you access to the outer class from any inner class.
It's an access method, yes, but mainly this is. This because we have a private method over here referenced out by an inner class. The inner class, it's compiled inside the Java p-outer class $myInner class. And I have to reference from this myInner class a private method out of the other class. That's why the Java P compiler automatically adds this access method. These are called access methods. And what it does, it just receives a reference and to the current, and it calls the foo. This way, I can provide access to private methods out of the class. It's valid only for the inner classes that refer private methods belonging to the outer class. Yes, for everything which is private and should be accessed from the external. Another quiz for you. We had initially this interface, my printer interface. I compiled and disassembled the code. And if we are looking over the disassembled code, I can spot it out. It has two methods, mainly the print method and another method. I slightly renamed this method because otherwise it is too trivial for you. But keep in mind we have something $0. The question is, how is that possible? How is that possible to have a private static method inside an interface? Moreover, how is that possible to have this kind of methods with the declaration of the code inside an interface? It's for Java 8 for sure, yes. Yes, very good spot, yes. It's because first we have a default method which is acceptable only in Java 8. This is half of the answer. The second answer is why we have private static.
I think that's to resolve the constant initialization when they're not primitive types.
Not really. Any other guesses?
It will contain the actual implementation.
Sorry?
It will contain the actual implementation of this.
Yes. You are on the right way. Exactly. Let's see what we have. I have this my printer interface, and because of the Java opt allows me to declare default methods in an interface, I can afford to declare this print method in my interface. Inside the print method, I have a lambda. expression. All the lambda expressions are desugared into this kind of lambda $0. That's why I told you initially I rename a bit the method, because otherwise it would be too obvious. And my lambda method, what it does an invoke virtual to system.out print line hello vox Bucharest. It's exactly what I have here. So all the lambda expressions are desugared into private methods. Now, if it is static or not depends on the context. And my print method over here, it's desugared into an invoke dynamic, which is resolved during the runtime by a lambda metadata factory. This is how it works at the bytecode level. Good. Let's continue and let's see what we have next. Let's discuss a bit about the execution engine. Before going deep into that, I can share with you two rationals. So in the hotspot, there are two rationals. The first rational is in regards with weak generational hypothesis. With what it means? It means mainly that during the process of allocating new objects, most of them become unreachable soon, and there are just a few objects from the old generation that refers the young generation. This is the first one. The second one is only during the runtime in the hotspot, the hotspot itself, it's allowed to prove and take the best optimizations. And this kind of rational influence the way execution engine works. The execution engine, it's mainly based on the interpreter and just-in-time compiler. If we take a look briefly over the architecture of the JVM, we have the class loader over here that loads all the bytecode. There are as well there is some verification. All the methods are initially interpreted, and it is compiled. Only what is worth it to be compiled, we will see what it means. And the compiled code is pushed into the code cache. Code cache, it's a dedicated memory area out of the native code. It's C heap that contains the native code. Let's explain why we have the interpreter initially in the hotspot. It's because of some practical aspects. For example, if we have to compile everything from the startup, from the very beginning, it will take a lot of time to compile everything. That's why they decided to delay a bit the process of compilation. More than that, in reality, not only all methods are quite frequently used. That's why it doesn't make sense to compile all of them, because we will have during the runtime a very big footprint, a very big code cache size, and we'll spend a lot of time for the startup. That's why the solution is let's focus on only what it's worth it to be focused. I mean only on those methods that are frequently called and used, and let's initially start in interpreter mode. And the process of compilation, it's mainly triggered by an invocation threshold. It mainly says that every time a new method it's invoked, the invocation threshold is increased, and once it reaches a specific size, it is compiled. And that method becomes a hotspot method. That's why the name is called HotSpot JVM. Yes?
This invocation threshold is a fixed number, or can
It's defaulted. It's defaulted. For example, we can slightly change it. For example, in case of client, there is lower. It's 1.5K invocation, and for the server, it's a bit higher. Let's see how it looks like. In the process of compilation during the just-in-time compiler, we have mainly the source code compiled by Javac. It goes into the bytecode, and it is compiled by the just-in-time compiler in the native code shape. The process of compilation during the runtime is extremely complicated, because the bytecode it's mapped to an intermediate representation. First, it's mapped to a high-level representation, in regards with the front-end compiler. After that, it's mapped into a low-level representation for the back-end compiler. It is profiled a lot of optimization occur during the runtime. There is also a profiler in regards with that, and at the end, there is the native code. In the HotSpot JVM, there are two shapes of just-in-time compiler. The first one is called client, or C1. The client provides fast code execution of acceptable quality. What it means, it's able to compile the bytecode quicker, and it doesn't do any assumption. It optimizes the code only if it can prove that optimization. It doesn't need a profiler, and the compilation threshold is 1.4K invocation. We have the second shape of it, it's called C2. For the C2, we reach highly optimized code, but this C2 does a lot of assumptions, a lot of optimizations, and a lot of the optimizations during the runtime. But it is able to reach the fastest code. The best optimized code are achieved by this C2. It needs a higher threshold compilation because it has to create more and more method invocations. It needs more information during the runtime, but the output of it's more optimized code. And we have a mixture between these two, which is called tiered mode. It's defaulted, at least on the latest JVMs. It starts in interpreter, it goes to C1 without profiling, with basic profiling, with full profiling, and it reaches C2, which is the server. Initially, I was trying to say there are quite a lot of optimizations, and the process of compiling the code during the runtime, it's really complex. Here, as you can see, are extremely large number of optimizations that occurred during the runtime. Let's focus only on few of them. Dynamic devirtualization. What it means. For example, during the runtime, if there is one interface that is implemented by one class, and the just-in-time compiler sees only one implementation for that interface, it maps it switches from a virtual call from a virtual method call to a monomorphic call. And it proves for fast method invocation, because during the runtime there is no more time spent in actually finding the target implementation. After a while, if the just-in-time compiler decides, okay, there is one more, probably there is one more class that implements the same implementation, but initially the just-in-time compiler didn't see it, it saw only the first one, it is able to de-optimize the initial optimization and probably re-optimize it back again. Yes? It's done during the runtime, not during the class logging. It's quite a complex process. There are used some sort of V-table, so it's quite a complex process, but the answer is yes, during the runtime, not during the class loading. Okay, so we end up probably with some de-optimization. What happens if after a while the just-in-time compiler spots there is a third implementation? What do you think? Very good, yes, yes. It de-optimizes again and re-optimizes it back, and it becomes a megamorphic call. Intrinsics, during the runtime, just-in-time compiler does a lot of optimizations in regards with these intrinsics. It mainly inserts the best native code specific to the target hardware platform. Few examples for that, it's compare and swap, equals, array copy, hash code, all of these are intrinsics. And we have another one, which is method inlining. Mainly, it replaces the target method with the code. that defines that method on the caller. Why it does that? Because it saves some pushing and popping of the frames on the stack, and it's quite quick. Here we have some JVM arguments. For example, if we want specifically to disable the just-in-time compiler, we have this compiler java.compiler equal none. None if we specifically want to run only by client or server, we have these two. This one is default. Here compilation is the default one, starts in interpreter, goes through client and reaches server. -x batch, what it does. -x batch basically says, don't do my compilation during the runtime as a background process, but put it as a foreground process. And it gives us a better deterministic behavior. Print compilation for printing the time, what was compiled, print inlining for seeing what was in line. If we want to see the compile time span, this is the option. Max inline size is quite interesting one because by default, the methods bigger than 35 bytes are not inlined anymore. So be careful with the code that you write because if the methods are too big, they are not inlined by default. Now, the question is how we can check the native code out of the bytecode itself, because by default, the HotSpot can't give us such possibility. We have, in addition to get this HSDs to compile on our target platform, for example, on Linux, on Unix, there are some specifics, and we add this one in top of the hotspot, and right after that, we are able to see the native code that is dumped. By default, hotspot doesn't have such possibility. More than that, we have to launch the JVM with unlock diagnostic VM option and print assembly. Now it's time for a demo. I have prepared two cases for today. The first one is to discuss about direct versus getter and setter method invocations from interpreter and mixed and tier compilation perspective. Okay, let me switch to the EV. Okay. No? Okay, never mind. So what we have here, basically I'm creating two threads. Inside each thread, I'm doing some computation from 0 to 1. So basically I do a sum. The difference between the first and the second is I'm doing the sum by using a counter. In one case, I have direct access to that counter because the counter is wrapped into an object. And for the other case, I have access to the counter by getter and setter method. And so this is the only difference. Other than that, the code is perfectly similar. And if I have to run this with initially by default, 1 second, yes, it's by default, without any JVM argument. Okay, what we have now. Apologize if the font is a bit small. I'm not sure if it is visible till back of the room now. Okay, I'll try to describe what happens. For example, I printed out the number of invocations and how much time it takes to do a direct field access per iteration and the time it takes for getter and setter field access. If we if we throw away the first invocations because those are full of noise, we end up at the end with the same time access. Even if we are using a getter and setter or a direct field access, the just-in-time compiler is able to do a few optimizations in order to benefit and to align the throughput for each. Mainly what happened, it did inlining, it did the optimizations, and so forth. So there is no such difference. If we have to run again the same code using by disabling the just-in-time compiler, initially we ended up with 3 nanoseconds for each. If we disable the just-in-time compiler and if we run only in the interpreter, it will be a bit slower, for sure. And what we have in this case, even the HotSpot was able to do a lot of optimizations accepting native code. That's why we have here 64 nanoseconds per one iteration in case of direct field access, and we have here the same 68 nanoseconds. It's around the same for getter and setter. Mainly the difference is in the native code. In this case, we don't benefit of any native code because we rely only on the interpreter. Okay, the second scenario is for this. So we discussed about direct versus getter and setter, and the second scenario is, let's take a bit focus on monomorphic, bimorphic, and megamorphic virtual method calls. And for that, I have another source file. What I have basically, I have a shape. It's an abstract class, and my shape is extended by a square that does the area. It's extended by a rectangle that does the area as well, and it's extended by the right triangle. What we have, mainly I have a parent class extended by 3 possible implementations during the runtime. And I'm just triggering inside doTest method. I'm triggering in a loop the area multiple times up to a certain specific number of iterations. The thing is that I have to slightly split this testing into a warm-up phase and real measurements intervals phase. And I'm using 3 instances of the same shape. Let's see what we get. So it's here by default. Let's see how it goes without any JVM argument specified. It takes a bit because I have a quite big number of iterations. So it was able, in the first place, it was able to create a square area, and one iteration took 5 nanoseconds. It continued with a rectangle, and in this case as well, we have nanoseconds per iteration. The funny thing is that in case of right triangle, we have 9 nanoseconds per iteration, which is bigger. So the first 2 took 5 nanoseconds. The third one took 9 nanoseconds. This is during the warm-up phase. If we continue the measurements, we see here for the square, it doesn't take anymore 5, but this time it's 8. If we continue with the rectangle, we have again 8. And in case of right triangle, we'll have the same. It's going to be finished. Oh, yes, we have the same. So the question for you, how's that possible? How's that possible? Some inconsistencies, let's call them this way.
Maybe because the index table with the methods has grown larger. When it's loading the method, the new class is de-optimizing and deciding.
Yes, exactly what we have discussed. When the just-in-time compiler sees only one implementation, it does a specific number of optimization. with the second shape, with rectangle, it de-optimized what was previously optimized and re-optimized it back. The thing is that starting with the third implementation, at this point, it knows there are 3 implementations during the runtime, and it doesn't do any more inlining. So during during the runtime, the just-in-time compiler, starting with the third implementation, it doesn't do inlining anymore. That's why here, during the real measurements, we have more robust results. The JVM, the just-in-time compiler, reached a steady state. He knows all the possible implementations during the runtime. The interesting thing is, if we, for example, do with print compilation, we will, for example, see what was compiled, what wasn't. Yes, thank you. I forgot the minus, sorry. Okay. Okay, let's run it again. Okay, so here we see it's a bit verbose. The first column stands the number of milli since the JVM has started. The second column stands for compilation ID. This percentage stands for on-stack replacement, which basically says if I have during the runtime a long-running loop, that loop is paused and it is compiled, and the method is replaced on the stack with a compiled version. Here we have the method that was compiled. This one is the just-in-time level for the compilation, remember, from 0 to 4. And this made not entrant, it's a proof that the just-in-time compiler did a lot of optimizations and the optimization. When it says made not entrant, it's in fact put it away for a while what I have previously compiled, because I discovered some new things. If it is not anymore used, it becomes zombie and it is thrown away out of the code cache. And here, if we focused on the start real measurements intervals, we see here that the just-in-time compiler doesn't do a lot of assumptions and the optimizations, because here it reached the steady phase in comparison to the previous one when it optimized and de-optimized a lot. Okay, let's continue what we have next. I don't encourage you, yes, in reality, that's the point, but I don't encourage you to do that, because the just-in-time compiler is sufficiently smart to do that for you. Okay, let's continue with the JITWatch. Have you heard about the JITWatch? No, it's really a fantastic tool that, apologize again for the font. It's created using JavaFX, and it's able for, in the left panel, I have the initial source, in the middle, I have the bytecode, and on the right side, I have the assembly code. And it's quite a fantastic tool that it's easier for us, for developers, to inspect the bytecode and the assembly code, all of this in the same place. So I quite encourage you to do that. And here, in case of bimorphic call, we see this area method was inline. This is what it says here on this pop-up label. And in case of megamorphic call, for the entire 3 implementation, my area wasn't anymore inlined. So starting with the 3rd implementation, the just-in-time compiler do not do any more inlining. I prefer to take all of the questions at the end because I think I'm running out of time. This is the last slide. So just to sum up, I would like to end the presentation with few advices for you. If you are passionate about doing microbenchmarking, but not only for the microbenchmarking, please avoid measuring in interpreter, because the interpreter is full of noise. If you know how to do some warm-up iterations, do them by choosing the appropriate number of iterations. And ideally, it will be to have short cycles for those warm-up iterations, and as well be aware of that just-in-time compiler optimization, optimization of virtual calls, inlining, and on-stack replacement. Thank you very much. That was all. If you have some questions, you can have me again.